Alright, in this video I'll be solving my 9709 Pure 3 October November 2025 guest paper. But before we get into it, I just want to kindly ask you to subscribe to this channel if you find the videos that I make for A-level math useful. I know it might not seem like much to you, but to me it goes a long way and it means a lot to me, so I'd appreciate it if you could just subscribe. Otherwise, let's get into it. Just to preface this, if you hear me sneezing or coughing, I've got a bit of a cold, so forgive me. You know, we still have to do maths even if we're sick, so let's get into it. Number 1. The polynomial x cubed plus ax squared minus 5x plus b, where a and b are constants, is denoted by p of x. It is given that x plus 3 is a factor of p of x. When p of x is divided by x plus 2, the remainder is equal to 3 times the remainder when p of x is divided by x. Find the values of a and b. Okay. So the ideas at play here are going to be your factor and remainder theorem. So recall that your factor theorem states that if a polynomial p of x is divided by a factor, say x minus a, then we know that p of a is equal to 0. This is the factor theorem. If you divide p of x by x minus a and x minus a happens to be a factor, then we can say that p of a is equal to 0. And then we also have the remainder theorem, which in truth is the one I should have written first, because the factor theorem is kind of like a special case of the remainder theorem. The remainder theorem states that if a polynomial p of x is divided by x minus a, then the remainder is equal to p of a. So I hope you can see that if you divide p of x by a factor, the remainder has to be 0. Okay, so in other words, maybe so that it's easier to read, I could have written this. Then p of a is equal to the remainder. And so the factor theorem just becomes a special case where the remainder is 0. So these are the two ideas we want to use in solving this question here. So keep that in mind. Here we've been told that our polynomial p of x has a factor, which is x plus 3. So according to the factor theorem, it says that if x minus a is a factor, then p of a is 0. So x plus 3 is a factor. Be careful with your signs. It's p of negative 3. So in other words, whatever makes this bracket equal to 0, x plus 3 equals to 0. X has to be negative 3. So this has to be 0. This is what we get from the factor theorem. And then we're also told that when p of x is divided by x plus 2, so we know that we're going to get information about whatever makes this bracket 0, that's going to be x is negative 2. So according to the remainder theorem, this p of negative 2 has to be equal to whatever the remainder is. And we're told that the remainder is 3 times the remainder when p of x is divided by x. Okay. So that means that's 3 times p of 0. Because if you've got x there, that's the same as x plus 0. Then using the same idea we've been using here, x has to be 0. I hope that makes sense. So the second part is from the remainder theorem. When we divide p of x by x plus 2, the remainder is p of negative 2. When we divide p of x by x, the remainder is p of 0. But we've been told that this remainder is equal to 3 times this remainder. And from here, you just substitute into p of x and you simplify for 5 marks. Quite generous if you ask me. Let's start with p of minus 3 is 0. So p of x is this function here. So we're substituting x with minus 3, so minus 3 cubed plus a times minus 3 squared minus 5 times minus 3 plus b, and we know that this is all equal to 0. So minus 3 cubed, that gives us minus 27, plus a times minus 3 squared, that's plus 9a, minus 5 times minus 3, that's positive 15, plus b is equal to 0. Okay. And now let's simplify this. That's going to be 9a plus b. Let's simplify this first before we move it to the other side. So negative 27 plus 15, that's going to be negative 7 plus 5, 12 is equal to 0. So you get 9a plus b is equal to 12. And then we're going to do the same thing. We're going to take p of negative 2. So you're substituting x with negative 2. So I'll do it here. That becomes negative 2 cubed plus a times negative 2 squared minus 5 times negative 2 plus b is equal to 3. Maybe let's just shift that down a bit. So that's equal to this 3 here multiplied by p of 0. Okay. So p of 0, you're just substituting x with 0 there. So you get 0 cubed plus a times 0, which is just going to be 0, minus 5 times 0, which is again 0, plus b. And so let's simplify this. Negative 2 cubed, that's negative 8, plus a times minus 2 squared, that becomes plus 4a, minus 5 times minus 2, that's plus 10, plus b is equal to 3 times b, so 3b. Let's simplify. We've got 4a, then 10 minus 8, so plus 2 is equal to, move that there, so 3b minus b, that's 2b. And so now I hope that you can see we've got two equations in terms of a and b, and we can solve those simultaneously and get our answer. So I'm just going to make a subject of the formula in this red equation because we're already close. So 2b minus 2, divide both sides by 4. We get that a has to be a half b minus a half. And then we can just substitute this a here with a half b minus a half. So you get 9 times 1 over 2b minus 1 over 2 plus b is equal to 12. So 9 times a half b, that's 9 over 2b. 9 times negative a half, negative 9 over 2 plus b is equal to 12. And now we want to make b subject of the formula. We've got 9 over 2 plus 1. That gives us 11 over 2b. Move the negative 9 over 2 this side. 12 plus 9 over 2. That gives us 33 over 2. 33 over 2. And then here to make b the subject of the formula, you can just, we want to eliminate this fraction here. So you just multiply both sides by the reciprocal, or just the flipped version of the fraction. So multiply both sides by 2 over 11. And so you get b is equal to, these twos would cancel and you've got 33 over 11. So b has to be 3. And substitute into here, you get that a has to be half of b, which is 3, minus a half. So a is equal to 3 over 2 minus a half, which is 2. So we can conclude that therefore A is 2 and B is 3. That's your final answer. I think it's not a difficult question if you know the factor and remainder theorem. It's a giveaway, to be honest. So make sure to learn those theorems. Number 2, the positive numbers m and n are such that the natural logarithm of m over n is equal to a, and the natural logarithm of m cubed n is equal to b. Express the natural logarithm of m to the 5 n squared in terms of a and b. Okay. So the way I want us to approach this is eventually we're going to create some sort of simultaneous equation in terms of the natural logarithm of m and the natural logarithm of n, but that's going to be a bit difficult to see. So we're going to create some sort of substitution so that it's easier on the eye. But first, what we're going to do is to just break this down so that it's in terms of ln m and ln n. Okay. So we know that ln m to the 5 n squared can be written as ln m to the 5 plus, since they're multiplying, ln n squared. And then I want to drop the powers. So we know that this can be written as, you drop the 5 ln m plus, drop the power here, 2 ln n. And what we're going to do is we're going to solve for ln m and ln n in terms of a and b. And that should give us an expression for this in terms of a and b. Okay. So now let's just forget about this for a second. We're now here. So from there, we're given that ln m over n is equal to a. We know that from our laws of logarithms, ln m over n can be written as ln m minus ln n. And this is equal to a. And I want us to do the same thing for this. That there can be written as, well, that's ln m cubed n is equal to b. Using laws of logarithms, that's going to be ln m cubed plus ln n, and that's equal to b. And here we can drop the power, 3 ln m plus ln n is equal to b. And here we're going to create a substitution. Remember, our end goal is to get ln m and ln n in terms of a and b. That's the whole idea behind the solution. But here it's a bit messy, so let's clear it up so that we can clearly see that this is a simultaneous equation in terms of ln m and ln n. So we can say something like, let x equal ln m and y equal ln n. So wherever there's a ln m, you're replacing it with x. Wherever there's a ln n, you're replacing it with y. So that what we end up with is x minus y is equal to a from the first equation. And then from this equation, we've got 3x plus ln n, which is y, is equal to b. And now we've just got a simultaneous equation in x and y. So we want to, so remember a and b are constants. These are just like numbers like 2 and 3. So these are not actually variables. So don't think, oh, we've got 4 unknowns here, we're solving for 4 things. No, we're just solving for x and y in terms of a and b. So keep that in mind. Okay. So we can make x subject of the formula in the first equation. We get x is a plus y. And then we can substitute it into the second equation so that it's 3 times a plus y is equal to b, multiplied through 3 times a, that's 3a, 3 times y, that's 3y, plus y equals b. And so 3a plus 4y is b. And here we want to solve for y. So 4y becomes, subtract 3a on both sides, you've got b minus 3a. Divide both sides by 4. You get y has to be b minus 3a over 4. And so we can come back to x here. Since we now know what y is in terms of b and a, we can come back to x and solve for x in terms of b and a. So x is a plus y, which is b minus 3a over 4. b minus 3a over 4. Okay. Maybe let's just put everything on one common denominator here. So 4, and then that becomes 4a plus b minus 3a. And if you simplify this, got 4a minus 3a, that's just a, and that's plus b, and that's over 4. And remember, what did we say? We say that let x equal the natural logarithm of m and y the natural logarithm of n. So if x is equal to a plus b over 4, that means the natural logarithm of m is equal to a plus b over 4. And if y is b minus 3a over 4, that means the natural logarithm of n is equal to b minus 3a over 4. And we can go back to our expression here, because this is what we're trying to solve for in terms of a and b. And we'll substitute our natural logarithm of m there and our natural logarithm of n there. So that's what, 5 the natural logarithm of m plus 2 natural logarithm of n. So we can just substitute in here. We know that this here is a plus b over 4. So that's 5 times a plus b over 4. Plus, we know that this here is b minus 3a over 4. So we've got 2 times b minus 3a over 4. Let's just simplify this. So in the first one, in fact, we can put everything over one common denominator, right? Because 4 and 4 here. And then I'm going to multiply through this first bracket. So 5 times a, that's 5a. 5 times b, that's 5b. 2 times b, that's 2b. 2 times minus 3a, that's minus 6a. And so if we simplify like terms, we get that 5b plus 2b, that gives us 7b. Then we've got 5a minus 6a, that gives us minus a. And this is all being divided by 4. And so we can conclude that finally, therefore, the natural logarithm of, what was it? M to the 5n squared. The natural logarithm of m to the 5n squared is equal to that. And that is your final answer. Number 3. On an Argand diagram, shade the region whose points represent complex numbers z, which satisfy both the inequalities. The modulus of z minus 1 minus 2i is less than or equal to 3, and arg z minus 3i is between negative 3/4 pi and 1/4 pi inclusive. Okay, so for starters, let's draw our complex plane. So we're going to draw our imaginary x's first and then our real x's. Label your x's. And I want us to start with this, right? What we're going to do is we're going to factor out a negative sign here. So if we take out a negative sign, that becomes 1, that becomes plus 2i. And so now you can interpret this as a circle with center 1 and 2i, and radius is equal to 3. But it's crucial that you factor out a negative sign here, because if it's not a negative sign, you can't interpret it in that way. So factor out a negative sign, get the coordinates of your center, and you know the radius is the constant that's on the other side. So what we're going to do is we're going to draw the circle. We've got 1 unit in the real axis, and we've got 2 units in the imaginary axis. And make sure to use a, what's the device? I always mix them up. Make sure to use your compass to draw the circle. So we want a circle with radius 3, something like that. Let me just adjust this. Okay. This is going to be your circle with radius 3 and center 1 and 2i. When they say less than or equal to 3, they're saying that the distance between z and this complex number has to be less than or equal to 3. So the distance between z is the circumference of the circle, and 1 plus 2i is the center of the circle. So they're saying that the distance between the center and the circumference has to be less than or equal to 3. So in other words, we're saying that we want the region that's inside the circle. And since we're saying less than or equal to, including the circumference of the circle. So the reason we need this negative sign, it tells us that we're looking at the distance between z, which is the circumference, and the center of the circle. And we want this distance to be less than or equal to 3. So less than 3 is everything that's inside the circle. Because can you see if I draw a line from the center of the circle to inside the circle, this distance here is going to be less than 3. Okay, and less than or equal to 3, so it means we can also include something that lies on the circumference, because that's going to be equal to 3. Okay, so essentially you just end up shading the whole circle. But let's not shade just yet, because we need to satisfy this inequality. So for that inequality, we've got negative 3 over 4 pi less than or equal to the argument of z minus 3i. Again, you're going to need to factor out a negative sign. And in this case, notice that your complex number there does not have a real part. So in other words, what you have there is 0 minus 3i. So when you factor this out, this negative sign out, it becomes 0 plus 3i. Right, so we've got 0 plus 3i. And this is less than or equal to a quarter pi. Right, and now what you're going to do is you're going to go to this point 0, 3i. So that's 0 units in the real axis and 3 units in the imaginary axis. So somewhere there, let me mark it right there. And you're going to draw a dashed line that's parallel to your real axis. And what we want to do is we want to draw these angles. All right. So we want to draw, we'll start with the positive one. We want to draw an angle of a quarter pi. If you convert this to degrees, you'll find that a quarter pi is 45 degrees. You can convert to degrees by multiplying by 180 over pi, which should give you 45 degrees. And then you can use your protractor to open up an angle of 45 degrees from this point that we've marked. So we can open 45 degrees, and you can tell the examiner this is 1 over 4 pi. And we're going to do a similar thing here with negative 3 over 4 pi. Negative 3 over 4 pi has to be negative 3 times 45, which is negative 135. So if I go straight down, that's 90. So 1 35 should be somewhere here. This has to be negative 3 over 4 pi. Again, use your protractor to open up your angles. And once you're done, now you can try to figure out which region we want. Here we're told that our argument has to be between negative 3/4 pi and 1/4 pi. So in other words, we want this whole region here. That's there. And be careful, always check, are they including the boundaries, these lines that are restricting your regions, are they being included? Since we're saying or equal to in both instances, then we're going to include them. If not, you would have used a dashed line to show that we're not including the boundaries. But now you can just go ahead and shade this whole region, because remember the first inequality is saying inside the circle and the second inequality is saying between these two angles. So both of them has to be inside the circle and between these two angles. And that's that area that I've shaded. And that will be your Argand diagram. Let's go on to number 4. The parametric equations of a curve are x is equal to e to the cosine of t and y is equal to 5 cos squared t. Find the equation of the tangent to the curve at the point E5. Give your answer in the form y equals mx plus c, where m and c are exact. Okay. Whenever you see parametric equations, think differentiation, because you learn parametric differentiation or implicit differentiation in Pure 3. So most of the time it's either one of those two, apart from maybe when they ask you for a quotient where you have to differentiate, apart from maybe when you have to differentiate using the product rule or the quotient rule. And in that case, it's typically a stationary point question. Okay. So what you're going to do is you're going to differentiate each of these two equations. And the reason we want to differentiate is so that we can find dy dx. Remember that dy dx is your gradient function. It gives you the gradient of the tangent to the curve at any point on that curve. And since here we want the equation of a tangent to the curve, it makes sense for us to get dy dx, because dy dx will allow us to find what m is. And then once we know what m is, we can simply use this set of coordinates to find c. So let's start with x is equal to e to the cosine of t, and we want to differentiate this. So dx dt is equal to, so remember here we've got an outer function and an inner function. So what I've put in brackets, maybe let's put it in red. So what I've put in brackets, that's our inner function. So to differentiate, first start by differentiating the outer function. So the outer function, that's the exponential. So if we differentiate the exponential, that's just e to the cosine of t, and then the rule says differentiate the inner function. So now let's differentiate cosine of t. If we differentiate cos, we're going to get negative sine. So be careful with that. And that negative sine t will multiply your, maybe let's write it on the other side. It looks a bit weird this way. So we've got e to the cosine of t multiplied by negative sine of t. So differentiate the outer function, that's the e, you just get another e with the same power. And then differentiate the inner function, that's cosine of t, you get negative sine t, multiply by that. That's your dx dt. And then now we have to do the same, differentiate y equals 5 cos squared t. So y is equal to 5 cosine squared t dy dt. Again, we can view this as a function inside of a function. So if I just move this power to, so that I've got this. Okay. So what I've put in brackets, that's the inner function. The outer function is the one that's raised to the power 2. So how do we differentiate? Using the power rule. Drop the power, so the 5 is still there, then drop that 2, your bracket remains, and subtract 1 from the power. So 2 minus 1, that just becomes 1. And now differentiate the inner function. So differentiate cosine of t, you're going to get negative sine of t. And that's your dy dt. Let's just clean it up. So that becomes dy dt is equal to negative 10 sine t cos t. All right, perfect. Now that we've got dx dt and dy dt, we can go ahead and find dy dx. So dy dx is just going to be, you can write it as dy dt divided by dx dt, right? Because the dt's would just cancel out and you end up with dy dx. So that means dy dx therefore has to be dy dt, which is that negative 10 sine t cos t, and then your dx dt has to be that, or rather we evaluated it to be that negative e to the cosine of t times sine t. And here the negative signs just cancel out. And so now what we have is dy dx, but note that your dy dx is in terms of t. Since we have dy dx, we can use this to get the gradient of the tangent at any point on this curve. We just need to know what the value of t is at that specific point on the curve, and then we can get the gradient. Okay, so we've been given information. We want the tangent at x is equal to e, so we can use x is e to help us find what t should be at that point. So if x is e, then we get that e has to be equal to e to the cosine of t. And we can just take the natural logarithm on both sides. The natural logarithm of e to the 1 is equal to the natural logarithm of e to the cosine t. And so you get that 1 is equal to cosine of t. And then t has to be arc cos of 1. And so t has to be equal to 0. And so now we can take this value of t that we have and substitute it into dy dx, and that should give us the gradient of the tangent to the curve at this point here. Okay. Just notice that we can actually simplify our dy dx here because we can cancel out sine t. And so we'd end up with 10 cosine t over e to the cosine t. Okay, perfect. And so now dy dx at t is equal to 0. This is just fancy notation for saying I'm finding what dy dx is at t is equal to 0. That becomes 10 cosine of t, t being 0, divided by e to the power of cosine of t, t being 0. Remember, cos 0 is 1. So this becomes 10 over e to the cos 0, so e to the 1, 10 over e. That's our gradient at this point, right? So I'm just going to make a note. M is equal to 10 over e. In our y equals mx plus c here, we found what m is. And now what we can do is to just use this set of coordinates as well as our value for m to find what c is. So we have the coordinates e5, we have e5, and we have m is 10 over e. And so we want to use that to find what c is. So we can substitute y is 5, x is e. So 5 is equal to m is 10 over e times x is e plus c. And so that would cancel out. And so you get 5 equals 10 plus c. And so that means c has to be 5 minus 10. C is minus 5. And so you can conclude that therefore the equation of the tangent to the curve at that specific point is y is equal to our gradient 10 over e x minus 5. And that's all you have to do to get 6 good marks. I think the trick is in actually just, first of all, actually understanding the idea behind the question, and secondly, being capable of differentiating these functions, because it's a bit tricky. Just make sure you understand how to differentiate a function inside a function, right? Because we had that same idea in both x and y. Before we go on to number 5, I just want to mention that I tutor AS and A-level math students. So if you're an AS or A-level math student who is looking to improve your grade to get maybe your B's, A's, A stars to get into your dream university, then make sure to click the first link in the description down below to book a free call with me. And then from there we can discuss and see how best I can assist you to get your dream grade so that you can get into your dream university. All right, number 5. By first expressing the equation tan x minus 45 degrees is equal to 2 cot x plus 2 as a quadratic equation in tan x, solve the equation for x is between 0 degrees and 180 degrees. Okay, so make sure your calculator is in degrees. And now let's proceed. We've got tan x minus 45 degrees is equal to 2 cot x plus 2, and they want us to express this as a quadratic equation in tan x. So what this means is that they want something of the form a tan squared x plus b tan x plus c is equal to 0. That's what we're trying to simplify this to. And then once we have it in that form, we can simply solve the quadratic equation and get our values. Okay, so the first thing we can do is to rewrite cot x in terms of tan x, because we can tell that our desired outcome is for everything to be in tan x. So we know that cot x is identical to 1 over tan x. So we can rewrite this as tan x minus 45 degrees is equal to 2 over tan x plus 2. And then here we've got what we call a compound angle. We've got x minus 45 degrees. So whenever you want to simplify a compound angle, you use compound angle formulas. So if you go to the MF19, you should find that tan of A, in this case it's minus B, is going to be tan of A minus tan of B. And this is over 1 plus, be careful with the signs, tan A tan B. Okay, so that's the compound angle formula we're going to use to simplify this. So in our case, our A becomes the x and our B becomes the 45 degrees. And you just substitute. So that becomes tan x minus tan 45 degrees. And this is all over 1 plus tan x tan 45 degrees. And this has to be equal to 2 over tan x plus 2. Okay, so punch into your calculator tan 45 degrees. You should find that that is equal to 1. So you get tan x minus tan 45, which we said is 1, over 1 plus tan x times tan 45. Tan 45 is 1, so that just becomes tan x. And on the right hand side, I want to put everything all over tan x so that we can cross multiply. So this becomes 2, and then that's plus 2 tan x. And so now we can just cross multiply. This multiplies that, that multiplies that. So we've got tan x times tan x minus 1 is equal to 2 plus 2 tan x times 1 plus tan x. And now we can expand our brackets. So tan x times tan x, that's tan squared x. Tan x times -1, that's minus tan x. And on the right, 2 times 1, 2, 2 times tan x, 2 tan x. 2 tan x times 1, 2 tan x. 2 tan x times tan x, 2 tan squared x. And now let's put everything on one side. I think I'll move this stuff to the right because I want the coefficient on tan squared to be positive. Okay. So that becomes 2 tan squared x, which is this there, minus, we've got positive 1 tan squared this side, so it becomes minus 1 tan squared x. And then I'll just move this minus tan x to the other side, it becomes plus tan x. And then we've got this plus 2 tan x. Oh, should have added that, plus 2 tan x. And then we've got the plus 2 there. And this is all equal to 0. Okay. So simplifying 2 tan squared x minus tan squared x, that's just tan squared x. Tan x plus 2 tan x plus 2 tan x, that's 5 tan x. Plus 2, and that's equal to 0. And so now, I hope you can see that we've got a quadratic in tan x, which was the first step in solving this problem. Once you have that, you can solve your quadratic, and then you should get solutions in terms of tan x, and then we can solve those for x. So you can't factorize this by side, so let's use the quadratic formula. So tan x is equal to minus b, b is 5, plus or minus the square root of b squared, so 5 squared, minus 4, a is the coefficient here, which is 1, c, that's 2, divided by 2 times a is 1. And so if we punch this into the calculator, start with the -1, -5 minus root 5 squared minus 4 times 2 divided by 2. This gives us -5 minus root 17 over 2. And so the positive one should give us that tan x is equal to -5 plus root 17 over 2. And from here, oh, we've run out of space. From here, we have to solve for x. So starting with this equation there, we can say that x is equal to arctan of -5 negative root 17, and that's over 2. With your calculator in degrees, evaluate arctan of, oh, mine's still in radians. Evaluate arctan of -5 negative root 17 over 2. This gives you negative 77.6350. So this is also called our principal value. So the value that you get straight from your calculator, that's your principal value. Here the interval they've given us is that x has to be between 0 and 180 degrees. Clearly this -77.6 is not within that interval. However, specifically for tan, you can use the following formula to get your other solutions. Oh, you probably can't see that because of my face. So we can use the formula PV plus 180 N. This is assuming 1 degrees. If this is radians, change the 180 to pi. So if we evaluate this at n is equal to 1, you're going to say your principal value, which is that value, plus 180 times 1. So I've got my principal value plus 180 times 1. That gives me 102.365. And this is clearly within the interval they've given us, right? 102.365. If you try this at n is equal to 2, you find that your solution, the next solution will be outside of the interval. So this is the only solution we get from this equation here that satisfies that interval. So now let's come back to this equation and see what solutions that gives us. So we're going to do x is equal to arctan of, that's negative 5 plus root 17 over 2. Again, punch this into your calculator, and this is going to be your principal value. This is arctan of negative 5 plus root 17 over 2. That gives you negative 23.6749, which is again outside of 0 to 180 degrees. So we can use the same formula at n is equal to 1 and say that here our PV plus 180 times 1 gives us, what does that give us? So PV plus 180 times n gives us 156.325 degrees. And so here we can go ahead and conclude that therefore x is equal to, you round it off to 1 decimal place, so 102.4 degrees, and the other solution is 156.3 degrees. Number 6. The diagram shows a circle with center O and radius R. The angle of the minor sector AOB of the circle is x radians. The area of the major sector of the circle is twice the area of the shaded region. Part A. Show that x is equal to 2/3 sine x plus 2 pi over 3. Okay. Let's digest what they've told us here. So we know that the angle of the minor sector AOB is x radians, that's fine. The area of the major sector of the circle is twice the area of the shaded region. So major sector would be from O to B. It's major, so it's the big one, to A. This is the major sector. And we're saying the area of, so major, let me write that down, major sector OAB, the area of that is equal to twice the area of the shaded region. So to get the shaded region, it's going to be minus sector OAB minus the triangle, because minus sector OAB is this whole pizza shaped red thing that we have here. So to get the blue shaded region, we just have to subtract the white triangle from the pizza, right? So it's going to be 2 times minor sector OAB minus the triangle OAB. That's what this is telling us. So now we just need to figure out the actual areas, or rather an expression for the areas. So we know that sector area is given by half r squared theta. So if the minor angle A or B is going to be x, remember that our angle should add up to 2 pi if we go a full circle. So we can say that the major angle here is going to be 2 pi minus x. And so substituting into here, we can say that our area is half. We've been given that our radius is r, so half r squared. Our theta is 2 pi minus x. And this is equal to 2 times our minus sector A or B. It's a sector, so it follows the same formula. So half our radius is still r, so half r squared. Our theta is x, so half r squared x, minus triangle OAB. So the area for a triangle we want to use here is going to be half AB sine C. So that means you need the angle between two sides of a triangle as well as the lengths of those two sides. So in this case, if we look at our triangle, we know that, let me just draw it on the side. We're looking at something like this, where both these sides are r. This angle here is x. So we can say that this is A, that's B. So it's half r times r sine of x. So half r times r is just r squared times sine of the angle between those two lines, which is x. Okay. And now it's just a case of trying to manipulate this to get to what they want. And so I'm just going to hold off on the left-hand side. I think I'll expand the right first. And let's see if we can come up with a general idea. So if we multiply 2 times half, we're going to get 1. So that just becomes r squared x. If you multiply 2 times half again, that just becomes 1. So that's minus r squared sine x. Here I can tell that in the expression we're going to, we don't have any r squared in it. So I see that all three terms have an r squared. So we can just divide through by r squared. So if you divide through by r squared, you're going to get half times 2 pi minus x is equal to, that's just now the r squared is gone, so x, r squared is gone there, sine x, excuse me, and I think I'm going to multiply both sides by 2 because I can see there's a 2 next to the sine x, and I know that I need to keep this 2 on the pi because of that. And so it feels natural for me to multiply both sides by 2. So let's do that. We get 2 pi minus x is equal to 2x minus 2 sine x. And now it is a question of making x the subject of the formula. So we have to put these two together, and then everything else should be on the other side. So I'm going to write this as 2x, which is on the right hand side, and bring this minus x that side, so it becomes plus x. And this is equal to, we've got the 2 pi on that side, and now the minus 2 sine x is coming this side, so plus 2 sine x. Maybe to match them, let's swap the order of these two. So that's 2 sine x plus 2 pi. And now, if we add 2x plus x, we get 3x. This is equal to 2 sine x plus 2 pi. Divide both sides by 3. So you'd end up getting x is equal to 2 over 3 sine x plus 2 over 3 pi. And that will be the final answer for part A. Part B. Show by calculation that the root of the equation in A lies between 2 and 3. So by equation in A, they mean that equation there. So let's just copy that down. So they're saying that the root or the solution to this equation lies between 2 and 3. So for us to be able to verify this, we're going to move everything on one side. So I'll just move the x to the right hand side. And then we'll call this function f of x. So we can say let f of x equal 2 over 3 sine x plus 2 over 3 pi minus x. And then we're going to evaluate f of 2 and f of 3. And if there is a sign change, that means there has to be a solution. So f of 2 is equal to 2 over 3 sine of x being 2 plus 2 over 3 pi minus x is 2. So if we punch that into the calculator, this is 2 over 3 sine. Make sure you are in radians, because they have told you here that your angle x is in radians. So make sure you're in radians. And anytime you're dealing with some form of circular measure, we always use radians in A levels. So make sure you're in radians. So switch your calculator to radians, and you want to evaluate 2 over 3 sine of x. X in this case is 2 plus 2 over 3 pi minus 2. That gives us positive 0.7006. And we'll do the same for f of 3. So that's 2/3 sine of 3 plus 2/3 pi minus 3 is equal to. So now x is 3. We get negative 0.8115. And so notice that there is a change in sign. So we can conclude that, therefore, since there is a change in sign, there is a change in sign. This conclusion is important, by the way. If you don't write this conclusion, you don't get the final mark. Since there is a change in sign, a root or the root lies between 2 and 3. Part C, use an iterative formula based on the equation in A to calculate this root. Correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Okay, so the equation from part A is that equation there. And we want to convert that into an iterative formula. So that means the x on the left becomes xn plus 1 is equal to 2/3 sine of, wherever there's an x on the right, you're going to put x. Let me be consistent with my xn plus 2 over 3 pi. And so here, since we don't have an initial value, we can just say let x0 be, we can use either 2 or 3, or we can use the midpoint of 2 and 3. But basically, a good starting point would be whatever x value you see yields a value that's close to 0 exactly. So here, I might actually favor starting with the midpoint of 2 and 3, because that looks like its function value would be much closer to 0. Because basically what's going on here is you're looking at it's positive at 2 and negative, so something like this. Your function is something like this. We notice that at 2, the function value was positive 0.7006. And then at 3, we notice that the function value was negative 0.8115. So what we're looking for is what is the x value that makes this function equal to 0? Because that is the solution of that equation. Right. So I hope you can see from this illustration, it looks like our value or our final answer should be closer to around 2.5, the midpoint of 2 and 3. So here I'm just going to say let our initial value x0 be 2.5, but you can start with either 2 or 3. It just might take a bit longer for you to get the solution. You might have to do a few more iterations. So if we do x1, it's going to be 2/3 of sine of x0, x0 being 2.5, plus 2 over 3 pi. And if we punch this into the calculator, this is 2 over 3 sine, again, we're still in radians, of 2.5 plus 2 over 3 pi. And that gives us 2.493. They want each iteration to 4 decimal places, so 3, 4. Maybe let me say that this is approximately. Doesn't really matter. Let's just trying to use the correct notation. But don't worry too much about that. Go on to the next iteration, x2, 2/3 sine. And here, instead of us, we know that here we want to put the value of x1, which is this value. So we want to always use the exact value. So don't put in the rounded off value here. Otherwise, your iterative formula might not converge, which is a problem because we want it to converge so that we get our answer. So what you can do is there's a button on your calculator that's written ANS. So wherever you had your 2.5 or your 2 or your 3, whatever value you used, yeah, don't delete anything in your calculator. Just go back to that 2 or 3 or 2.5 and you're going to replace that with ants. So that now what you have in your calculator looks like this. 2 over 3 sine of ants plus 2/3 pi. And from there you can just press equals. And you should get 2.49. This is 6.9. So what the answer function is doing is it just stores the value of your previous answer, which is also the value of your previous iteration in this case. And yeah, if we round both x1 and x2 to 2 decimal places, see that it's not quite there because x1 is 2.49, whereas x2 would be 2.50. So we need to go again. Let's do x3. That's 2/3. In this case, you don't have to keep writing this since we've already written 2/3 sine of ans. Answer, remember, has the previous iteration, so you can just don't change anything on your calculator, just press the equal sign. You should get the result of the next iteration. So now I'm getting 2.4950. And hopefully you can see that this here is approximately 2.50 and this is also 2.50. So our sequence there has converged. So we can conclude that therefore the root is 2.50. Because remember, you only stop when you've got 2 consecutive iterations that have the same value correct to whatever degree of accuracy they've specified. In this case, you stop when you've got 2 consecutive iterations that have a value correct to 2 decimal places, which is the same. Number 7, find the complex number z for which z plus 7 over z plus 7i is real and the modulus of z is equal to root 37. Give your answers in the form z is equal to x plus iy, where x and y are real. Okay, this is a bit of an interesting question. So I think let's start here. want you to recall that if you've got a complex number z is equal to x plus iy, the modulus of z is equal to the square root of x squared plus y squared. Okay, so in this case, they have given us that the square root of x squared plus y squared is equal to root 37. The square root of x squared plus y squared is equal to root 37. And so if we just square both sides, we get that x squared plus y squared is equal to, that should be 37 up there. Okay, so that's what this bit of information is telling us. It gives us this equation here. And so our job then becomes to use this bit of information, this bit of information to come up with the second equation in terms of x and y. And once we have that, we're just going to solve it simultaneously with this equation that we got. And so we get what x and y are, and therefore what z is. So they have told us that z plus 7 over z plus 7i is real. So what that means is that the imaginary part of this thing, if you are to write this, let's say you've got z plus 7 over z plus 7i. If you are to write this in its Cartesian form, the form x plus iy, that should be of the form a plus iy. In this case, your imaginary part is going to be 0 because we've been told that it's a real number. Remember, all real numbers are just complex numbers with an imaginary part that's equal to 0. So what we can do here is find what the imaginary part is here, and then we equate it to that. Because remember, there's a rule that states that two complex numbers are equal if and only if both their real parts are equal and their imaginary parts are equal. So if we find the imaginary part of the left-hand side, we know that it should be equal to 0. So let's do that. So we've got z plus 7 over z plus 7i. Remember that z is also x plus iy, so I'm going to write it in that form. So we get x plus iy plus 7 over x plus iy plus 7i. So the top part, so that we just combine the real parts, that's x plus 7, that's your real part, and then you've got your imaginary part, iy. And on the bottom, your real part is just the x, and then your imaginary part is going to be the iy plus 7i. So let's factor out the I, and so that's y plus 7. If you have two complex numbers dividing each other, if you want to write them in Cartesian form, what you have to do is to multiply both the numerator and the denominator by the complex conjugate of your denominator. So let's do that here. So if I put a square bracket there, square bracket there, the complex conjugate of your denominator is just flipping this sign there. So that's going to be x minus I y plus 7. And so the numerator has to be multiplied by that as well. Y plus 7. Okay. So in the back of your mind, just keep it in mind that this is all equal to a plus 0i, right? So now what we're going to do is we're just going to expand everything. I know it looks messy, but let's do it. Maybe for simplicity's sake, let's group this, keep this together as the real part. So when we're expanding, let's do x plus 7 times the x plus 7 times the x, and then we've got the same bracket again, but now with the I bracket. So that becomes negative I y plus 7, and this is multiplying the x plus 7 bracket. Okay, and then we're going to do the same with IY. So first multiplied by x, and so you're going to get plus xyi, and then iy times the negative I times y plus 7. So that's going to be negative I, there are two i's here, so I squared, and then you've got y times y plus 7. And this is all being divided by, we've got complex conjugates on the bottom there. If your original complex number is a plus bi and your conjugate, then your conjugate has to be a minus bi. So if you multiply a complex number by its conjugate, you're going to get a difference of 2 squares. Right? So that just ends up being a squared minus bi squared, which simplifies to a squared minus b squared I squared. Remember, I squared is minus 1, so that just becomes a squared minus b squared times minus 1, which is plus b squared. So on our denominator, if we can just figure out what a and b are, we can easily simplify that. So a has to be this x, and then b has to be here y plus 7. So it means our denominator is simply x squared plus y plus 7 squared. That's your denominator. And here again, this is all equal to a plus 0i. And so now what we're going to do, remember our interest here is mainly in the imaginary part from the left hand side. So we want everything that has I. So we know that I squared is equal to negative 1. So I know that here we have I squared, that's negative times negative 1. So I just end up with a plus, and this becomes real, plus y times y plus 7. And so hopefully you can see that our imaginary part is going to come from here. And of course, it's going to be divided by that. So let me just write that out. Our real part is the x plus 7 times x plus the y times y plus 7. And if we distribute the denominator, that's going to be divided by the x squared plus y plus 7 squared plus, now our imaginary part, that's the stuff I have put in this red rectangle. That's going to be our right xyi first. We've got xy, and then that's negative. Remember, we factored out the I, so negative y plus 7, x plus 7. Negative y plus 7, x plus 7. And this is all being divided by the x squared plus y plus 7 squared. And we know that this has to be equal to a plus 0i. And so I hope that you can see that this is the real part, this is the imaginary part. We know that our imaginary part has to be equal to 0. We don't really care too much about the real part, because I mean that equation is not going to lead to anything useful. It's going to be in terms of a as well, so we don't want to mess with that. So going back to that idea that two complex numbers are equal if and only if both their real parts are equal and their imaginary parts are equal. So that means that this imaginary part here has to be equal to that imaginary part. And so we can say xy minus y plus 7 x plus 7 over x squared plus y plus 7 squared is equal to 0. You can drop the i's on both sides because they're common. And now hopefully you know that your denominator can never be 0. So the only way this is 0 is if the numerator is 0. Otherwise, if denominator is 0, then you get a 0 division error, right? Which we don't want. So now you end up with this equation: xy minus y plus 7 times x plus 7 is equal to 0. Maybe let's just expand that out. So we've got y times x, that's xy. Got y times 7, that's 7y. 7 times x, 7x. 7 times 7, 49. And this is all equal to 0. So we've got xy minus xy minus 7y minus 7x minus 49. And this is all equal to 0. Xy and xy cancel out there. So you've got minus 7y minus 7x minus 49. I said x, but I wrote y. Minus 7x minus 49 is equal to 0. And so now we have our second equation in terms of x and y. And if we come back to the top here, notice that we now have our two equations in terms of x and y that we can solve simultaneously. So if we start with the second equation here, we can rewrite this as 7x plus 7y is equal to minus 49. So just moving these two to the other side. And so let's make x subject of the formula. 7x is minus 49 minus 7y, divide through by 7. You get that x has to be equal to minus 49 over 7 minus 7 minus 7y over 7 minus y. And then we can substitute this x here with that. Okay. So what we end up with is minus 7 minus y squared plus y squared is 37. Expand this out, minus 7 squared is 49. 2 times minus 7 times minus y, that gives us positive 14y minus y squared, that's plus y squared. And that's also plus y squared, and this is 37. And so you end up with writing it in order of decreasing powers of y. Let's start with the power. Let's start with the y squared. That's 2y squared plus 14y plus 49. Bring the 37 to the left, minus 37 is 0. So 2y squared plus 14y. 49 minus 37, that is 3 plus 9, 12. Is equal to 0. We can divide through by 2. Y squared plus 7y plus 6 is 0. And now we can factorize. Do not use the quadratic formula, factorize. So y is equal to 0. Factors of 6 that add up to 7. So that's positive 1 and positive 6. So either y is negative 1 or y is negative 6. So what does that mean for x? X is minus 7 minus y. So when y is negative 1, you get that x is minus 7 minus minus 1. So x is equal to minus 6. And when y is minus 6, then you get x is minus 7 minus minus 6. And so x is equal to minus 7 plus 6, which is minus 1. And so we can come to the conclusion that, therefore, remember z is of the form x plus iy. So z is equal to negative 6, negative 1i. Negative 6, negative 1i, or z is equal to negative 1, negative 6i. Negative 1, negative 6i. And that will be our final answer. To be honest, really here, you don't need to show all this working. Once you get to this rectangle here, hopefully you should be able to see that this is your imaginary part and that has to be equal to 0. And so that's where you should get this equation that we got here. And so you don't really have to simplify and clearly separate everything. I just wanted to separate it out for you so that you can see that this is my real part, this is my imaginary part, and so my imaginary part has to be 0. And so you get your second equation, solve the two simultaneously, you get x and y and therefore z. Number 8, with respect to the origin or the points A and B have position vectors negative 4i, negative k, and negative I, negative 2j, negative 3k respectively. The line L1 passes through the points A and B. Part A, find a vector equation for the line L1. Okay, so the vector equation of a line can be written in the form R is equal to A plus lambda B, where A represents the position vector of a point on the line, and B represents the direction vector. So when we say point on the line, it can be either point A or point B. It doesn't matter which point you use. You can use any of them. And then direction vector. Since our line is going through the points A and B, our direction can be AB. And so to get AB, we can say OB minus OA. And OB being our negative I, negative 2j, negative 3k, minus our OA, which is the negative 4i, negative k. Negative 4i, negative k. And so you get that AB is equal to, that's negative I, negative 2j, negative 3k. If we multiply through by the negative sign, that's plus 4i minus minus k, so plus k. And so AB has to be negative I plus 4i, that's 3i, negative 2j, there are no other j's, so just negative 2j, and then negative 3k plus k, that's negative 2k. And so this is the direction vector of our line. So we can conclude that the vector equation of our line is R is equal to A. A is the position vector of any point on the line, so we can use negative 4i, negative k, or negative I, negative 2j, negative 3k. I'll use negative 4i, negative k because it's simpler. Negative 4i, negative k, plus, so this is just a variable, so plus lambda, and then our direction. Our direction is 3i minus 2j minus 2k. And this here is the vector equation for line L1. Now we're given that line L2 has equation R is equal to 2i minus 5j minus 7k plus mu minus 3i plus 3j plus k. Part B, show that L1 and L2 intersect. Okay. So what we're going to do is we want to solve these two lines simultaneously. And so what we'll get are 3 sets of equations, and we need to check that all 3 sets of those equations are satisfied. And if they are satisfied, it must mean that our 2 lines intersect. If they're not satisfied, then they do not intersect. So to do that, let's maybe start off by rewriting this in column vector notation, because it's then easier to see what's going on. So if I rewrite the line L1, the equation becomes, so the point, I want to write this in column vector form, that's negative 4, and then we don't have a j component, so that's 0, and then negative k, so negative 1, plus lambda, the direction is 3 minus 2 minus 2. Minus 2, and we want to do the same for L2 as well. R is equal to, that's 2 minus 5 minus 7 plus mu, and then negative 3, 3, 4. Negative 3, 3, 4. Okay. And from here, I want us to write the parametric equations of our line. So for L1, the x component is going to come from, say, -4 plus lambda times 3. -4 plus 3 lambda. The y component is going to come from saying 0 plus lambda times -2, so -2 lambda. The z component is going to come from saying -1 plus lambda times -2. So -1 plus lambda times -2 becomes -1, -2 lambda. And we'll do the same for L2. So the x component will come from saying 2 plus mu times -3, which is 2 minus 3 mu. The y component will come from saying -5 plus mu times 3, so -5 plus 3 mu. And then the z component will come from saying -7 plus mu times 4, -7 plus 4 mu. And so now we can equate the equations for x, we can equate the equations for y, we can equate the equations for z. So we end up with -4 plus 3 lambda is equal to 2 minus 3 mu. -2 lambda is equal to -5 plus 3 mu. And then -1, -2 lambda is equal to -7 plus 4 mu. So this is equation 1, that's equation 2, that is equation 3. And so what we're going to do is we're going to use two of the equations to solve for mu and lambda. And once we have mu and lambda, we'll substitute those values into the third equation that we haven't used, and both sides of that equation should be equal if these lines do in fact intersect. So I'm going to take equation 2, right? So let's use, I'll just write, using our equation 2, we have that -2 lambda is equal to -5 plus 3 mu. And I want to make lambda subject of the formula. So lambda is -5 over -2 plus 3 over -2 mu. So lambda is equal to 5 over 2 minus 3 over 2 mu. And then we can substitute this into the first equation, right? So using equation 1, we're going to replace this lambda with this expression here. So we've got -4 plus 3 times 5 over 2 minus 3 over 2 mu is equal to 2 minus 3 mu. And so let's simplify this. That's -4 plus 3 times 5, that's 15 over 2, minus 3 over 2 times 3 minus 9 over 2 mu is equal to 2 minus 3 mu. And then let's simplify on the left. We've got -4 plus 15 over 2, that is 7 over 2, and minus 9 over 2 mu is equal to 2 minus 3 mu. And so we end up with 9 over 2 mu minus 3 mu. If I move that side and move the 2 this side, is equal to 7 over 2 minus 2. So 9 over 2 minus 3 is 3 over 2 mu is equal to 7 over 2 minus 2. That's 3.5 minus 2, so 1.5, so 3 over 2. So if we divide both sides by 3 over 2, we should get that mu is 1. Okay. And so since mu is 1, we can find lambda. Lambda is therefore 5 over 2 minus 3 over 2 times 1. So lambda is 5 over 2, 5 minus 3, 2, 2 over 2. Lambda is 1 as well. So using equations 1 and 2, we get that mu is 1 and lambda is 1. So let's substitute this into the third equation and see if it holds. So using our third equation, we have -1, -2, lambda is 1, this should be equal to negative 7 plus 4 times mu. We found mu to be 1. So that's times 1. And so if we add up the left-hand side, we get negative 1, negative 2, that's negative 3. Is this equal to negative 7 plus 4, which is negative 3? Yes, it is equal. So we can conclude that, therefore, since all three equations are satisfied, L1 and L2 intersect. And that would be our final answer. Part C, find the obtuse angle between the directions of L1 and L2. Okay. So to do that, we can use the formula that says cosine of theta is equal to A dot B over the modulus of A times the modulus of B, where in this case, A and B represent the directions of L1 and L2. So we can start off by finding the dot product of the directions. What is the first direction? So the first direction is 3, negative 2, negative 2. So we've got 3, negative 2, negative 2, and the other one is negative 3, 3, 4, negative 3, 3, 4. So we've got 3 times negative 3, that's negative 9, plus negative 2 times 3, that's negative 6, plus negative 2 times 4, that's negative 8. So we've got negative 9 minus 6, which gives us negative 15, minus 8, which gives us negative 23. And now we need to do the product of their moduli. So we need to get the modulus of 3, negative 2, negative 2. This is going to be the square root of 3 squared plus 2 squared plus 2 squared. 3 squared plus 2 squared plus 2 squared. So that's 4 plus 4, 8 plus 9, 17. So that gives us root 17. And we'll do the same for the other direction. So we want negative 3, 3, 4. So that's just the square root of 3 squared plus 3 squared plus 4 squared. 3 squared plus 3 squared plus 4 squared. 4 squared is 16 plus 9, 25 plus 9 again, that's 34. Root 34. And so now at this point, we can just substitute into this equation here and solve for theta. So we have that cosine of theta is equal to the dot product, which is negative 23, divided by the product of the moduli. So root 17 times root 34. So divided by root 17 times root 34. And so theta has to be arc cos of negative 23 divided by root 17 times root 34. And if we punch this into the calculator, that's arc cos of negative 23 over root 17 times root 34. And this gives us 163.1 degrees. If you're in degrees, since they didn't specify here, you can use either radians or degrees. So we can conclude that our angle is 163.1 degrees. And it makes sense because they say the obtuse angle, which means it has to be between 90 and 180. Number 9. The diagram shows the curve y is equal to cos x sine squared 2x for x is between 0 and a half pi, and its maximum point m. Part A. Using the substitution u is equal to sine x, find the exact area of the region bounded by the curve and the x-axis. Alright, so to get the area under this curve between 0 and a half pi, which is what they want us to do, we have to integrate from 0 to a half pi. and we're integrating our curve, which is this function, cosine of x sine squared 2x with respect to x. No pun intended. And we're supposed to use the substitution, u is equal to sine x. So a good starting point, even if you don't know where you're going, is to just differentiate your substitution, because you always will differentiate the substitution. So du dx is equal to, if you differentiate sine x, you're going to get cosine of x. Okay, we'll come back to this bit. What I want us to do is to first simplify the sine squared 2x. Because notice our substitution is strictly for sine x. So we don't want to have any double angles, any 2x's. So we need to make sure that everything is either in cosine of x or sine of x. Because cosine of x, can you see, is very similar to the derivative of the substitution. So that's nice. So anything with sine x or cos x works for us. But we don't want any double angles like sine 2x. So if we look at what we have, we've got an identity sine 2x is equal to 2 sine x of cos x, right? This is the double angle formula for sine. It's in the MF19, but here we've got sine squared 2x. So that's this whole thing squared. Because remember, it's just convention to put the power 2 here, but this is exactly the same as saying sine 2x all squared. So which would be the same as 2 sine x cos x squared. And so we get that our sine squared 2x is equal to square the 2, or square the sine squared, square the cos squared, x, like that. So that's nice, because now it means we can rewrite this as the integral from 0 to half pi of, I'm just going to put cos x next to the dx, right? So I'll write the sine squared 2x first, which is this part. So 4 sine squared x cos squared x, and then we've got cosine x dx. So the idea here is that we want to keep a cos x here, because we know that when we then change dx to du, it's going to cancel out with the cos x that's coming from there. If you don't quite see it yet, just trust me for now, you see it. And so what we're going to do, it means this part here will naturally cancel out when we do our substitution, but this cos squared x, we have to find a way to rewrite this in terms of sine so that we can just use the substitution directly to sort that part out. So we know that cos squared x is identical to 1 minus sine squared x. So what we have is the integral from 0 to half pi of 4 sine squared x multiplied by cos squared x, which we said is 1 minus sine squared x. Sine squared x, and that's cos x dx. So now if we use the substitution u is equal to sine x, we have that the integral from half pi of 4, this sine x, we can replace it with u, but remember it's squared, so it becomes u squared, 1 minus this sine x again, replace with u, but it's squared, so u squared cos x dx. So because we are using the substitution u is equal to sine x, we want our whole integrand here to be in terms of u. So that means we want to end up integrating with respect to u. So we need to find a way to change this dx to du. When we differentiated our substitution, we got du dx is cos x. So that means dx has to be du over cos x. If you swap those two. And so that means we can replace this dx that we have here with du over cos x. And so this part here becomes, instead of dx, it's now du over cos x. And that cos x I was talking about earlier will cancel out like that. And so instead what you end up with here is just du there. But don't forget to also substitute your limits. So we had that x was 0 and x was 1 over 2 pi. We need to convert this to u. So u is equal to sine x. So u becomes sine 0, u is 0 for the lower limit. So we're still integrating from 0. And the upper limit, u is equal to sine 1 over 2 pi, which is 1. So now we're integrating from 0 to 1, and we're integrating 4u squared times 1 minus u squared with respect to u. So everything is now completely in terms of u. Our limits, our integrand, and also our du. And so at this point, you can just multiply and expand through this bracket. So we've got the integral from 0 to 1 of 4u squared times 1, which is 4u squared. And then 4u squared times negative 4u squared, which is negative 4u to the power 4 with respect to u. And we can go ahead and integrate this. So if you integrate 4u squared, it's going to be add 1 to the power, that's 3, divide by 3, minus 4u, add 1 to the power, that's 5, divide by the new power. And this is from 0 to 1. And so now let's substitute in our limits. So we'll start with 1, 4 times 1 to the power 3 over 3 minus 4 times 1 to the power 5 over 5. In this case, if we substitute 0 there, that will become 0. So you've got 4 times 0 over 3. So that's just 0 minus 4 times 0 to the 5 over 5, which is just 0 again. So it's really just this part that will give us the result. So if we punch that into the calculator, that's 4 over 3 minus 4 over 5, and that gives us 8 over 15. So it means that the area bounded by the curve and the x-axis, this whole area, is equal to 8 over 15. Part B, find the x-coordinate of M, giving your answer correct to 3 significant figures. 6 marks. Okay. So, in the question, we are told that M is a maximum point. So that means that M is a stationary point. And so since M is a stationary point, we know that dy dx has to be 0, right? This is the first thing that should come to mind when you see some form of stationary point. And so that means we're just going to find dy dx, equate that to 0, and so for x, that should give us the x-coordinate of M. Of course, the 6 marks isn't differentiating your function. It's not an easy function to differentiate. So that's cos x sine squared 2x. Okay. So we've got y is equal to cos x sine squared 2x. And we need to differentiate this. So hopefully you can see that this is a product. Okay. So the way we're going to do that is to say that first hold the first function. So hold the cos x, write it exactly as it is. Then we want to differentiate the second function. So differentiate sine squared 2x. And the way we're going to do that is to take this as sine of 2x all squared. So first bring down the power, that's 2 sine of 2x. Subtract 1 from the power, that's just 1. And then you're going to differentiate the inner function, which is sine of 2x. So first differentiate sine, you're going to get cos of 2x. Then notice that it also has an inner function, which is the 2x, so differentiate that as well. You get 2. Okay. So you first start with the outer function, then differentiate the inner function, and if there are any more inner functions, differentiate those inner functions as well. And so that just gives us 2 times 2, which is 4. 4 sine 2x cos 2x plus, now you're going to hold the second function, so sine squared 2x, and differentiate the cosine x. You differentiate cos x, you get negative sine x. And so we have that dy dx is equal to 4 cos x sine 2x cos 2x minus, because of this minus sign there, minus sine x sine squared 2x. And so now, remember we say dy dx is 0, so this expression here has to be equal to 0. So we can say that we can actually just factor out a sine 2x there, sine 2x, and then here we end up with 4 cos x. That sine 2x is gone. We've got cos 2x minus sine x, and now we're left with only one of the sine 2x's, sine 2x, and this is all equal to 0. And so either sine 2x is 0, which is this part, or that big square bracket is 0. 4 cos x cos 2x minus sine x. I want to rewrite sine 2x using the double angle formula. 2 sine x cos x, right? 2 sine x cos x is 0. Okay, we'll come back to this equation here. Let's see if we can simplify this further. So here, hopefully you can see that we can factor out a cos x, right? So we've got cos x, and then we've got 4 cos 2x, minus we've got 2 sine squared x is equal to 0. And so now we've got either cos x is 0, that's another equation that we will need to solve, or the bracket is 0. So 4 cos 2x minus sine 2 sine squared x is 0. And here we can use the double angle formula that says cosine of 2x is identical to 1 minus 2 sine squared x, because that allows us to convert everything to sine here, which makes it easier to solve our trig equation. So we can write this as 4 times 1 minus 2 sine squared x minus 2 sine squared x is equal to 0. And so that's 4 minus 8 sine squared x minus 2 sine squared x is equal to, so we have that 4 minus 10 sine squared x is 0. So 10 sine squared x is 4. And so sine squared x has to be 4 over 10, which is 2 over 5, or 0.4. Okay, so now we've got these three equations that we need to solve. I'll just start with the sine squared x is equal to 0.4. We can take the square root on both sides so that we have sine x is equal to plus or minus root 0.4, which gives us two equations. So either sine x is negative root 0.4, and so x is arcsine of negative root 0.4. X is equal to, are we in degrees or radians? We are in radians, and x has to be between 0 and pi over 2. Okay, so change your calculator to radians, and we want arcsine of negative root 0.4, which gives us negative 0.6847. Let's see what the positive gives us. So sine x is equal to positive root 0.4. X is equal to arcsine of root 0.4. X has to be, we do arcsine of that, root 0.4. That gives us 0.6847, which should be between 0 and pi over 2, because pi over 2 is approximately 1.57. And so this fits within our interval. Let's just check that the other solutions or the other equations we got here don't actually have solutions within the required interval. So sine 2x is 0 means that 2x has to be arcsine of 0, which is 0. And so that means x has to be 0. And we know clearly, we can tell from our diagram that our m is not at 0. So that's not the solution we're looking for. We do cos x is 0. We get x is equal to arc cos of 0. And x is pi over 2. And that's the other bound of the interval that we're interested in, right? Pi over 2 is there. So that's not the point that we're interested in. So it must mean the 0.6847 is the right solution. So we can conclude that therefore x has to be 0.68, what was it? 84785. I believe there are 3 decimal places, 3 significant here. That will be our final answer. Number 10, part A. Find the quotient and remainder when 2x cubed plus 3x squared minus 15x minus 24 is divided by x squared minus 8. All right. So we've got x squared minus 8, and this is dividing 2x cubed plus 3x squared minus 15x minus 24. So remember, you divide using the term with the highest power. So in this case, we're going to divide this polynomial using x squared. So we're going to say, how many times does x squared go into 2x cubed? That's going to be 2x. And so 2x times x squared, that gives us 2x cubed. Then 2x times minus 8, that's minus 16x. 2x cubed minus x cubed, that's 0. 3x squared, 3x squared. Minus 15x minus 16x, so that's 16x minus 15x, so plus x. Bring down the minus 24. How many times does x squared go into 3x squared? That's 3. So minus 3 times x squared, that's 3x squared. 3 times negative 8, that's negative 24. So 3x squared minus 3x squared, that's 0. Then we've got the x there. And then negative 24 minus 24. So that's negative 24 plus 24, which is just 0. So here we get that our quotient, we stop dividing here because the degree in our divisor is now higher than the degree in our dividend. So we can't carry on dividing. This x becomes a remainder. So we can say that the quotient is whatever you have on top there, 2x plus 3. And remainder is whatever you have at the bottom here is x. And that will be our final answer. Part B, the variables x and y satisfy the differential equation dy dx is equal to 2x cubed plus 3x squared minus 15x minus 24 over 4y times x squared minus 8. It is given that y equals 2 when x equals 3. Solve the differential equation to obtain an expression for y squared in terms of x. All right, so we've got a differential equation. the first step is to separate our dE, right? We want everything that is x on the right hand side and everything that is y on the left hand side. So it means this 4y, remember it's dividing here, so when it moves left, it has to multiply. So it becomes 4y dy. We're going to move the dx to the right. It's going to come there. It's dividing, so it comes and multiplies. So this is equal to 2x cubed plus 3x squared minus 15x minus 24. And this is all over the x squared minus 8 that we have there. And remember the dx that we said has to move this side. Once you've separated everything properly, not breaking any algebraic rules, we want to integrate both sides. Okay, so if you integrate 4y, raise the power here by 1. 1 plus 1 is 2, divide by 2. And then I'll also put my constant of integration here. On the right hand side, the integration is a bit more complex. So there are certain things that Cambridge does to help you out. So the reason we had part A here was so that we can use our results from part A to simplify this integration here. So hopefully you should know that when a polynomial is divided, the result you get is going to be the quotient plus the remainder divided by whatever your divisor was. So what we have here is our p of x over d of x, which is what we evaluated in part A. We did p of x divided by this. So this has to be equal to the quotient plus the remainder over the divisor. So what we're saying is that 2x cubed plus 3x squared minus 15x minus 24 over the x squared minus 8 is equal to our quotient, which is the 2x plus 3 here, plus the remainder, which is the x, divided by x squared minus 8. So instead of trying to integrate this, we can integrate this instead. So we can now write the right-hand side as the integral of 2x plus 3 plus x over x squared minus 8 with respect to x. And so now let's see how we can integrate that. In fact, let's maybe split it to the integral of 2x plus 3 with respect to x plus the integral, and then we'll do this part separately. X over x squared minus 8 with respect to x. So if you integrate 2x, add 1 to the power, that becomes 2, divide by the new power, 2. So you end up with just x squared there. If you integrate 3, add 1 to the power, it becomes 3x. Plus, now here, what we want to use is the idea that k, the integral of f prime of x over f of x with respect to x is equal to k, the natural logarithm of f of x. So what this is saying is that if you differentiate your denominator and you find that its derivative is the same as the numerator multiplied by some constant, then this integrates to just k ln f of x. So if we differentiate our denominator here, we get 2x, which is very close to being equal to our numerator. But we can force that and say let our numerator be 2x and cancel out by multiplying by a constant half, because half times 2 is just 1. And what this does is that the denominator becomes f of x. If you differentiate f of x, you get 2x, which is now our numerator, multiplied by some constant, half, which allows us to use this. And so we can say that this becomes We just drop that there. This becomes half, which is our k, ln our f of x, which is the denominator, x squared minus 8. And so what we end up with is that we've got 4 over 2y squared, which is just 2y squared, plus c is equal to this integral, which is this result here, x squared plus 3x plus half ln x squared minus 8. And so now we can use the information they gave us in the stem of the question to figure out what c should be. We're told that when y is 2, x is 3. So we can substitute y with 2. 2 times 4, 2 times 2 squared, plus c is equal to x is 3. So 3 squared plus 3 times 3 plus half ln 3 squared, which is 9 minus 8. So 2 times 2 squared, that's 4 times 2, which is 8, plus c is equal to 9 plus 9, which is 18. And then there we've got plus half ln 1. You should know that ln 1 is 0. If you don't, now you know. A plus c is equal to 18. C is equal to 18 minus 8. So c has to be 10. And so we have that coming back to this equation there. 2y squared plus 10 is equal to x squared plus 3x plus a half ln x squared minus 8. And they specified that they want an expression for y squared in terms of x. So they want us to make y squared subject of the formula. So this becomes 2y squared is equal to, we have to move the 10 to the other side. So x squared plus 3x minus 10 plus a half ln x squared minus 8. Then divide through by 2. So y squared is equal to x squared over 2 plus 3 over 2x minus 10 over 2, which is 5. A half divided by 2, that's a quarter, ln x squared minus 8. And that is the solution to our differential equation. Number 11, find the exact value of the integral from 0 to a third pi of x squared sine of half x dx. 6 marks. Okay, so these are two functions multiplying each other. So you're going to have to use integration by parts here. We want to integrate from 0 to a third pi. In fact, I'll just drop the limits for now. We'll come back to the limits. Let's just focus on getting the integral of this. So the integral of x squared sine a half x dx. So remember, use late to decide what u has to be. In this case, we've got algebra, which is the A there, and we've got trig. So your u has to be whatever is higher up on that list. So u has to be the algebra. So we're going to say let u equal the algebra, which is x squared. So that means dv dx has to be the trig function, sine a half x. And so if we differentiate u, du dx, we get that if you differentiate x squared, that's just 2x. And now we want to integrate sine a half x. So if you integrate sine, you're going to get negative cos of a half x. And then differentiate the inner function, you get half. So that means you have to divide by half. Dividing by half is the same as multiplying by 2. So we can write this as negative 2 here. And so you have that the integral of x squared sine a half x using the formula for integration by parts, which is in the MF19, It says the integral of u dv dx with respect to x is equal to uv minus the integral of v du dx with respect to x. So we want uv, which is the product of those two. That's negative 2x squared cosine of a half x. And then minus the integral of 2x times negative 2. So I'll just multiply that negative sign by this negative sign to get a positive sign. So we just end up with plus 4x cos of half x. And notice that this here is still a product that we have to integrate by parts. So we're going to integrate 4x cos a half x dx by parts again. And the scenarios are the same. We've got algebra and trig, so let u be the algebra. U is going to be the 4x, and v dv rather dx has to be the cosine of half x. And so if you differentiate u, you get du dx. Differentiate 4x, you get 4. Integrate cos of a half x. So if you integrate cos, you get sine, that's of half x. And if you differentiate the inner function, if you differentiate a half x, you get a half. So we have to divide by a half, which is the same as multiplying by 2. So now we have that the integral of 4x cos a half x dx is equal to, that's going to be again uv, which is this time 2 times 4x times sine a half x, 8x sine a half x, minus the integral of v du, so minus the integral of 4 times 2 sine a half x, 8 sine a half x with respect to x. So the integral of 4x cos a half x dx is equal to, that's 8x sine a half x minus, we need to integrate this here. So we've got the 8, integrate sine, you're going to get negative cos. So that negative sign will multiply with that negative. And so it becomes 8 cos a half x. Differentiate the inner function, you get a half. So you have to divide by a half, which is the same as multiplying by 2. And so we have that the integral of 4x cos a half x dx is equal to 8x sine a half x, 8 times 2, 16 cosine a half x. We should technically be putting a constant here, but don't worry too much about the constant. We're going to eventually bring back our limits, so it would disappear anyways. So this here is the integral of 4x cos half dx. Remember, that was this part of our result. So going back to our problem, we're saying the integral of x squared sine a half x dx is equal to negative 2x squared cos a half x, negative 2x squared cos a half x, plus this result, which is what we have down here. So plus 8x sine a half x plus 16 cos a half x. And now we can bring back our limits. In fact, I think let's just factor out some common stuff. We can factor out a 2 throughout. And then between these two terms, I want to factor out a cos half x. It's not really necessary. I just think it will make life easier when we're now substituting limits. So cos a half x, the 2 has been factored out, the cos a half x has been factored out, so there's just a negative x squared there. And then here, a 2 has been factored out, that's 8. And then cos half x has been factored out, so plus 8. And then here, only a 2 has been factored out, so plus 4x sine a half x. You could have taken it exactly as this and then just substituted in your limits. I just want to reduce the length of our expression, which to be fair doesn't look that much shorter. But anyways, let's bring back our limits. We're integrating from 0 to a third pi. So this means that we've got 2, the integral. In fact, I could put them here, 0 pi over 3. And then we can just substitute in. So cos of 1 over 2 times pi over 3 times negative pi over 3 squared plus 8 plus 4 times x pi over 3 sine a half times pi over 3. And now we need to do the same for the lower limit, 0. So cos of half times 0, so cos of 0 times negative 0 plus 8. Let me put brackets here. And then plus 4 times 0. So this whole term will just become 0 since it's being multiplied by 0 there. Now let's simplify. So we've got 2 cos of 1 over 2 times pi over 3. So make sure you're in radians. We want cos of 1 over 2 times pi over 3. That gives us root 3 over 2. And this is multiplying negative pi squared over 3 squared. So negative pi squared over 9 plus 8. And then we've got plus 4 times pi over 3. So 4 pi over 3 multiplied by sine of a half times pi over 3. So we want sine of 1 over 2 times pi over 3, which is just 1 over 2, minus, so be careful here, it might be tempting to say cos 0 is 0, it's not. Okay, so minus, we've got cos of 0, which is going to be 1 times 0 plus 8, so 1 times 8 plus 0. So we've got 2, and then here root 3 over 2 times minus pi squared over 9. So that's minus root 3 pi squared if we multiply the numerators. And then the same for the denominators, 2 times 9, 18. And then root 3 over 2 times 8. So that's going to be root 3, 8 over 2, that's 4. So 4 root 3. And then here we've got plus 4 pi over 3 times a half. That's going to become 2 pi over 3. And then minus 8. And so we can just multiply through by 2. Here, that's 2 over 18, giving us a negative 9. So we've got negative root 3 over 9 pi squared. Then 2 times 4 root 3, that's plus 8 root 3. 2 times 2 pi over 3 plus 4 pi over 3. Then 2 times minus 8, that's minus 16. And this here becomes the final answer. I believe they wanted an exact value, so you kind of had to do the simplification manually, because most calculators would have given you decimal places if you tried to just punch this whole result into your calculator. All right, so I believe that is the last question as well. Yes. That is the guest paper. I hope you found this video useful, somewhat useful. If you did, please share it with your friends, share it with anyone else who is writing their exams. Yeah, I wish you the very best in your exams, and make sure to leave a like, subscribe if you found this video useful, because I know it might not seem like much to you, but genuinely, to me, it means a lot just for you to click that subscribe button. So just make sure to double check that you've subscribed. And if you're struggling with AS or A level math, make sure to click the first link in the description down below to book a free discovery call with me, and then we'll discuss how to help you get your dream grade so that you can get into your dream university. Thank you for watching. Goodbye.